Welcome back, I'm that chemist, and today we're going to be talking about thin layer chromatography. Hopefully this video will be a practical guide that can help guide you through your TLC experience. So you might have several different reasons for doing TLC. One reason would be to just see how a reaction's going. If it's gone to completion, what you can do is you can have three spots. You can have one spot where you spot your starting material, another spot where you spot your product if you have product, and a third spot where you would spot your crude reaction mixture. Now, if you don't have isolated product, another thing you can do is do a co-spot where you spot your starting material with your reaction mixture and just see potentially if there's any effect of the starting material on where the product would elute. Another reason you might use TLC is you're about to purify your compound using flash chromatography. So in this case, it's necessary to identify conditions which would be optimal for separation. Maybe not perfect, but at least suitable for purification. Additionally, once you've done your column chromatography and you've collected several different fractions, you might want to analyze those fractions using TLC. And so one thing that you could see with TLC is whether or not there's starting material in your fractions. Sometimes reactions produce multiple products, and in those cases, you might still need to identify whether or not your fractions have one product versus another product. This could happen if, for instance, you had a reaction which produced different diastereomers or different isomers, just depending on what can occur. So this is just a quick TLC guide. If you haven't done TLC before, this is the guide for you. So if you have no experience, a really good place to start is 20% ethyl acetate in hexanes. Sometimes people use cyclohexanes, sometimes people use pentanes, but if you're not sure what you're doing, just let's start with hexanes. And so what you do is you get a little reservoir like this one shown here, and you put in just a tiny little bit of solvent down there. Then about 1 centimeter up the plate that you're going to be doing your TLC on, you'll draw a line, and you usually would label which spot is which, and then you'll spot each spot with your different samples. And so normally the way I would do this is just get like a tiny little bit of your stuff that you're running. If it's crude from your reaction, maybe you would use a little bit more than 1 milligram, maybe use just like the tiny bit of the end of a pipette or something. And if you have a pure compound, then you just take like the tiniest crystal or like a milligram, but you'd never weigh this out. And then you put that in a test tube with something like DCM or acetone, whatever's convenient, and it just needs to dissolve your stuff and it needs to be volatile. And then you get a capillary, and so what I usually do is I will make a capillary from a pipette. From the thick part of a pipette, when you get it hot and you stretch it out really thin, you can get a nice little capillary. Then that capillary can be used to spot your compound. And normally what I do is I'll have like a little wash vial of like acetone or something, and then I'll clean out my capillary and reuse it. Now, not everyone will do that. Some people will just use a capillary once and throw it out. But I've had capillaries that I've made from a pipette that have lasted longer than 3 months if you take care of it. If you're interested in me doing a video in that in the future, I could do that. I just am not currently doing lab work. So additionally, it's worth noting that when you run your TLC plate, you have to stop it before the solvent gets to the end of the plate. So when the solvent's probably like half a centimeter or a centimeter from the top, you take it out with a pair of tweezers and you label with pencil on the top where the solvent front ended. And then that's how you know how much the solvent moved from the baseline to the solvent front. And so what you do if you're measuring RF, which is retention factor, is you're going to measure how far the analyte traveled up the plate versus how far the solvent front traveled up the plate. And then you divide the distance that your compound traveled by the solvent front, and that gives you your RF, your retention factor. Now, to visualize your spot, there's a couple different ways to do this. So one way is if you have a UV active compound, you could just use a UV lamp, which is able to excite your compound at a specific wavelength. Some UV lamps have multiple settings, and so sometimes those settings could be better for conjugated systems, like extended conjugation, something like a quinoline, or just something with like an alkene, potentially. Additionally, sometimes when you get TLC plates from different vendors, they have visualizers included in the matrix, inside the silica, and that just makes it easier to see. And so if you wanted to do a stain, one really easy stain, if you're not sure what you're doing, is to just do a KMNO4 stain. I'll include a prep for that in the description. And essentially what KMNO4 will do is it'll just oxidize stuff, and then what remains will be like usually a white plate. And that's just from the visualizer like indicating in that position where it's reacted, although the KMNO4 will form manganese dioxide when you heat it. And so that can also just be like visually seen in most cases. Normally when you have your wet TLC plate with stain still on it, it's important to put that on a paper towel. And something I didn't mention before, after you take your TLC plate out of the reservoir where you're running your TLC, make sure you let all of the solvent evaporate first. Additionally, when you're spotting your stuff, make sure that all the solvent that you spotted your compound with is fully able to evaporate. Now, you might wonder how many times you need to spot your stuff. I haven't listed here about how many times you spot with a capillary, but typically if I was spotting, I'd probably do 4 or 5 spots, but it depends on how dilute your solution is. If it's really concentrated, you might just need like the minimum amount possible. You might even need to dilute your stuff in your test tube more first. But if it's already like, decent-ish, you should be able to get away with 1 or 2 spots. But if your stuff isn't that UV active, or if it isn't that concentrated, you might need to spot more times. Okay, so the thing that you can do if it isn't working that well is, like let's say your separation's bad, you can just increase the amount of ethyl acetate if it isn't moving too much, or you can decrease the amount of ethyl acetate if it's moving too much, or if it isn't moving enough, rather. And so when you're doing TLC, what you essentially need to do is optimize separation. So if you're analyzing a reaction and you're just trying to see how done it is, you just need to make sure that the product is separated from the starting material so that you can actually clearly tell when it's done. Now, not all reactions go to completion, but this is a way to monitor what's happening without doing an NMR or mass spec of some sort. So normally the conventional wisdom, if you're going to be doing chromatography, is to find a system where your analyte that you're interested in, the compound you're interested in, has a retention factor of 0.3, which means if the length of the TLC plate is 10 centimeters, your compound would move 3 centimeters up the plate when the whole plate is run once. But I personally prefer to have an RF closer to 0.2. Just in my experience, if you do 0.3, sometimes separation isn't as good. If you disagree with that, please comment down below with what you think would be best. Now, I will also do my TLC plates slightly more polar. So if I'm optimizing for a column, I'll find conditions that give me 0.2, but if I'm analyzing fractions, I'll usually use a little bit more polar of a solvent system, just so it's easier to see stuff separate. Okay, so one thing that I'm going to highlight in a little bit is that low elution power, essentially like more hexane, less polar solvent, doesn't always mean better separation. And if you want to know more about why this happens, you can look into the analytical chemistry, the physical chemistry in the Van Demeter equation. And so if you can't separate 2 spots very easily, you might need to just screen a different solvent system. So even though we normally use ethyl acetate hexanes, sometimes you can use other solvents that I'm going to talk about in a slide or two. Now, most of the time, we don't get the correct solvent polarity on our first guess. If you've been doing TLC a long time and you have an idea of what your compound is exactly, you might be able to make an educated guess about what will work, but usually you still have to screen several sets of conditions to find suitable ones for your separation. So in my experience, I would say most of the time I still have to screen 3 or 4 sets of conditions, but sometimes you'll get lucky and get it on your first or second try. Sometimes, very rarely, I've had to screen stuff for like hours, which is very uncommon, but sometimes you'll get really stubborn separations where the product and the starting material or impurities just happen to have like really similar retention factors. Oftentimes, what you can do is if you have stuff coming off A first, B second, if you change the polar solvent to a solvent from a different solvent group, you can actually invert it. So maybe B will elute first and then A will elute second. Now, this doesn't always happen, but you'll run into cases where this can happen. And so sometimes if you have multi-component mixtures, this can be a really useful way to tune out one of the compounds which you're trying to isolate, which maybe is harder to isolate under whatever conditions you were using before. And so if you wanted to cut TLC plates, glass-backed TLC plates are one of the most common types. The second most common would be aluminum. And you can get these glass plates, and if you create a grid essentially based on the width of these plates, you can make like a little line indicator. You don't have to use line indicators. I just prefer to do this so that you get somewhat uniform sized plates. And then you score right to left if you're right-handed. If you're left-handed, you should score left to right, because this ruler is going to be going on top of this part you already scored. And so if you put it on the part that's already scored, it won't lay flat, and then you won't be able to get as clean of a line. So you do this on the horizontal axis, then you rotate it 90 degrees, and you do it on the vertical axis so that you get lines like this. Now, when you're doing this, you might actually prematurely get the plate to crack. So you can see this crack here is right along the line that we were cutting. But that's okay. That's not like an issue. So what you do is you take the part that's loose and you flip it upside down and you push into into the flat part. And so if you tried to do this the wrong side around, it wouldn't break as easily and it would be more likely to chip. But if you do it this way, normally you do this with 2 hands with fingers on either side of where the groove is, you should be able to cleanly crack it. So this just takes like a little bit of practice in terms of how deep to cut the groove. There are also tools available on Amazon or eBay, which cost like $300-ish, that can automate, or that can simplify at least, a lot of the scoring process. But you can get a cheap little tool like the one I showed in this last slide on Amazon for like $8 or less. When I started doing research, I could get one of these for like $1.50, but now they're a little bit more expensive. They just have like a diamond tip on them, and that's harder than glass, so it's able to score the glass. And then you just snap it, and it breaks right along where the groove is. And so you just go through and you do this for all the plates, making sure that you're pressing on the smooth side. You just need to be careful not to chip the silica, and then you can have a nice pile of plates. And if you don't feel like doing this, sometimes you can get undergrads to do this. And if you make it their lab job, they'll get really good at it. Okay, so aluminum plates are preferred by many people because they claim it's easier to cut them. Now, in my opinion, the sound that the scissors makes when you cut aluminum plates is like nails on a chalkboard. It's not too pleasant for me. But you can also use those like office paper trimmers, those things that are used to cut big stacks of paper. That can also be used. Just make sure you ask first, because people might not be happy about you contaminating their paper trimmer with silica gel or dulling their blade. And so this here, right here, you can see on the corner of these plates, you can see why the aluminum backed plates are inferior, in my opinion. Okay, so some miscellaneous images. Here you can see a heat gun. Sometimes when you do stains, you need to heat the stain to make it visualize. If you heat it too hot, you can destroy the stain and prevent any useful visualization. Sometimes you don't need to do stains. Sometimes you can use a UV lamp like this one shown here. Now, here's a couple pictures of various TLCs that have done for one or another reasons. You can see sometimes you're analyzing different fractions, like shown here. You can see there's different stuff visualizing, kind of crappy separation. Here you can see a case where product and starting material have the same RF exactly, but they stain differently. And so you can see fraction 4 here, even though it has an identical RF, you can see that eventually whatever this yellow stuff is separates out from the starting material, but the starting material is clearly still there in fraction 4. Maybe there's a little hint in fraction 5. Now in this one, you can see a crude reaction which just produces an absolute mess of stuff. Not a great reaction at all. And so here's a couple other ones here where you can see various TLC plates with poor separation. Okay, so KMNO4. KMNO4 is probably the most common stain. I polled YouTube and KMNO4 was by far the most popular stain. This can just react with anything that can get oxidized, and most TLC plates, when you buy them, come with a visualizer specifically made for KMNO4. Another one is iodine on silica gel. The way you make this is you just put some iodine in silica gel. Eventually it disperses its way throughout it. You can also heat it up and that'll accelerate the process a little bit, but once you prep that stain once, that will last for years. It's pretty rare that you need to even add new silica, or rather new iodine to that stain. It's a super easy stain. And so the rationale here is that iodine's nonpolar. If you have nonpolar compounds in your TLC, they will be concentrated enough on the plate that the iodine can dissolve in them. Once the iodine in the rest of the silica gel on your TLC plate evaporates, the only remaining iodine should be dissolved in your compounds, and this can visualize. I've also had some luck staining sulfur-containing compounds with iodine, and you just need to make sure you circle those spots before the iodine disappears. This is like a hit and miss one, but some people swear by it. Now, vanillin or anisaldehyde are both really good stains for lots of functional groups, especially nitrogen derivatives, but in general, like vanillin can produce colored products for different compounds. Anisaldehyde is also really good. I'd say anisaldehyde is probably a little bit better than vanillin, and it's a little bit more popular. Now, there's cerium stains which will stain almost everything. So ceric ammonium molybdate, Seebach stain is another really, really good one. There's also Hanessian stain. I don't know if I said that right. But those are the 3 kind of common stains that are used, and they can stain almost anything. I think Seebach is the most popular, at least in people I know anecdotally. They say this can stain anything, even if it's just got like alkyl CHs, Seebach will usually still work. Okay, and then a stain that I have created that's been really useful in my research is a silver nitrate stain. And so this is just some silver nitrate in a mixture of water and methanol, and this is able to visualize sulfur-containing compounds when gently heated. Sometimes for like thiocarbonyls, you don't even need to heat them. However, there's some links to other recipes that I'm going to include in the description. Some other ones include like, for instance, ninhydrin. Ninhydrin is like probably another common one that I should have included here. If you use ninhydrin a lot, make sure you comment down below. Okay, so I polled the YouTube audience, and most people use KMNO4 as their favorite TLC stain, followed by anistaldehyde vanillin, then cerium, and then other. And the 25% of you that are high schoolers didn't know what TLC was. Okay, so if you're doing a column, there's some common solvent systems. And so the most common ones are shown here. Methanol in a DCM or chloroform, really, really common. Ethyl acetate in hexanes or pentanes, etc., also really common, probably the most common. But you can also use ether or acetone in hexanes, and those can be really useful as well. Now, there's some specialized ones which, if you're trying to separate really polar stuff, some really stubborn separations, these can come in handy. And so one of them is to use a little bit of acetic acid, glacial acetic acid, not aqueous, just glacial, in ethyl acetate hexanes. This isn't perfect for every application because acetic acid might be too harsh. Additionally, if you're having issues with methanol DCM, you can use ammonium hydroxide in methanol, 10%, as like a solution to methanol, and then you do 1 to 10% of that solution in DCM or chloroform. If you're Figueroa, you can use methanol hexane agua. It's his favorite solvent system. Sometimes if you are using methanol DCM, which can go up to 10% usually, you can also use acetonitrile as a co-solvent to just get a little bit more polar push for your column. It's also known that you can use acetonitrile in chloroform. You can technically do combinations of any solvents, but these are just kind of relatively common ones that people that I've talked to have used. Also, sometimes people will deactivate their silica by pre-washing with triethylamine. Also, sometimes people will use triethylamine as an additive in their eluent, just like 1 or 2%. This can sometimes help prevent decomp, but it can also sometimes improve separation. So now let's talk about solvent groups. So solvent groups are a game changer because it classifies solvents into different categories, and it gives you an idea of what solvents would be worth trying next. And so the general rule of thumb is if you're trying to do a separation with a solvent from a given solvent group and it's not working that well, pick a solvent from a group as far away as possible. So if you're using dichloromethane as your polar solvent, so let's say dichloromethane hexanes, you'd want to go as far away as possible. So that would be like diisopropyl ether, diethyl ether, solvents in group 1, or like chloroform, solvents in group 8. Now you might think that DCM and chloroform are very similar, but you can see that they appear in different solvent groups. And on this chart over here, you can see that DCM is more of a dipole moment, and here they list chloroform as a weak proton donor. Okay, so the strength shown here is just like dissolving strength, how good it is at dissolving some molecules. You can see that something like hexane isn't a great solvent for most things, which is why its dissolving strength is low. But if we look at something like chloroform or acetonitrile or acetic acid, these are great solvents. And so sometimes if you're having a really challenging separation, it can be worth trying one of these out, and you might have a lot more success. Now, once I'd learned about this and I tried it myself several times, it was like a game changer to me. And so this is a couple pictures kind of illustrating this. So if this case here was like, let's say 40% ethyl acetate and you switched it to 20% ethyl acetate in hexane, you can see that in the original case, this was bad separation because everything just came right off the silica. Barely any interaction with the stationary phase, way too much of an interaction with the mobile phase, which is the eluent. Here you can see that there's a little bit more interaction with the silica, so it's able to separate out a little bit more. So what is happening is it's not affecting the selectivity of separation, it's just increasing how much time it can interact with the stationary phase. Here, though, you can see in this case, by changing the solvent group that you're working with, you can see that the ease of separation for certain compounds greatly changes. And this is because the solvent is interacting with the molecules more or less, and the molecules are having to interact with the stationary phase more or less. And so this is why the order that things elute can often, occasionally reverse. And none of these pictures show the full reversal of these compounds, but it is a thing that can happen. So it's definitely worth screening other solvent groups, especially if you have a challenging separation, especially if you have multiple components that you're trying to separate. Okay, so some quick and dirty rules. A nice rule of thumb is if you use diethyl ether, it's half as good at eluting as ethyl acetate. So 20% diethyl ether is about the same as 10% ethyl acetate. Now, I've also heard from people that acetone can be used as a surrogate for ethyl acetate. Sometimes you also get better separation. It's from the same solvent group as ethyl acetate, but it's different from diethyl ether. And so people have said that acetone is about half, or rather twice as strong as ethyl acetate. So if you use 10% ethyl acetate, you can usually get away with 5% acetone. And to just kind of reiterate this, if you had 100% diethyl ether, this would be the same as 50% ethyl acetate or 25% acetone. But obviously, depending on what functional groups you have in your molecules, this may not necessarily apply, but it's a good quick rule of thumb. Okay, so Not Voodoo X also has some other good advice if you have challenging separations, and I would really recommend this laboratory chromatography guide, which is just a free thing you can download from Buki, and they have a really good breakdown of how solvent groups work for purifications, and it's really practical. So hopefully this has been an entertaining video about TLC. If you like the style of video, please comment down below. It would really help out this channel if you left a like and subscribed, and I hope you have a great day.